Hello, can you hear me?
Yeah, I can hear you.
Okay. So first thing, do you have any question for the class, for the homework or assignment? Let me know. Any question?
I'm good.
No question. Okay. So basically, I just want to review a little bit this class. So basically, for this week, we think about the data representation. So you should have idea how the computer understand that when we enter the number 8.5, or when they enter the character A or B or C or D, right? So that everything is the data representation. So how can they understand what we give into the input here, what you give in the input. So for the number, yeah, we have some types of number. You have the integer, you have a floating point, like that. Right? So if you remember something about the number format here, you have multiple ways to represent the number. The first one is everything about the unsigned here. Right? You have unsigned number, unsigned integer. Sorry, unsigned integer here. So basically, for the entire integer, it's everything about 1, 0, 2, and 3 or something like that, and go on. Right? That is a whole number and a non-negative integer number here. So in the case of the unsigned integer number, it's very simple. Normally you just convert it from the decimal to binary. Right? So if you remember about the binary, it is a by 2, right? So it's by 2, and break it down in the column here. Break it down into column here. So the first column is the numbers, the number 0, number 1, number 2, number 3, 4, 5, 6, and 7 here. So think about if you have 1 byte, that means you have the 8 bits, and the bit number is everything from 0 to 7. And when working with the binary, it is by 2, right? So everything you have is by 2 here. You have 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3, 2 raised to 4, 5, 6, and 7 here. And from that, you have this one 1, 2, 4, 8, 16, 32, 64, and you have 138 here. Okay, so for the unsigned integer number, is everything non-negative and the whole integer number. So think about if you want to convert the number, if you want to convert the number 176 here to the unsigned integer number, you just convert it normally, right? You just convert it normally. So we think about that. Remember, when we want to convert from the decimal to the binary, you always have to working from the left to the right. So we have worked from the right. So when you compare from 176 here with 128, so whenever you greater than, you have a number here. So when we have number 1 here, that means you already have 128. So you have to minus over 128 here. So you have 48 left, right? Now if move to the right, you compare 48 with the 64, less than, you put 0 here. You still have 45 here. You move to the left, you move to the right again. You have a 48 here, greater than 32. So you put the number 1 here. Now you already have the 32 minus it to the 32 here. So you have 16 left. 16 left perfectly matches this one. Right? So you put number 1 here. Now you minus 16, you have 0 left. So that's why you have all of them 0 here. Okay, so in that case, that if you want to convert from the 176 to the unsigned integer number, you convert it to the 1, 0, 1, 1, 0, 0, 0, 0 here. Okay. And one thing about the definition, you also know about the overflow here, right? Overflow. So what do you think if you want to convert the number 300 here to the 8 byte here? You are not able to convert it. You are not able to store it 8 bit here. you are not able to store the number 300 into the 8-bit here, because you see, if you have the 8-bit, so you have the 2 raised to 8, you have the 256 value. So everything in the range from 0 to 255 only. Right? So you see the 300 here greater than 255. So in that case, you are not able to store 300 into the 8-bit memory. In that case, you have to store it into 16-bit memory here. So whenever you don't have enough memory, in that case, the code is the overflow here. Okay, so the first thing is everything about the unsize. The second format you study about is the size and magnitude here. Size and magnitude, right? So for the size and magnitude, you have 1 bit here for the size, one bit for the size here. And so all of the other bit is the magnitude here, right? So we can store it in the 8-bit or the 16-bit also, right? So think about, for the 1 bit of size here, if you have the positive number, it's a number 0, and if it's a negative number, it's a bit number 1 here. So that you have to remember that. And for the magnitude here, if you want to store in the 8-bit here, somehow if you don't have enough bit in the 8-bit, you have to insert a number 0 on the left of that. Right? So think about this one. If you want to convert the number 9 here, if you want to convert the number 9 into the size and magnitude, how we convert it? Let me know how we convert the number 9 in the size and magnitude format here.
Oh, what number is it?
Number 9.
Oh. Convert it to binary?
Convert it to size and magnitude format. 8-bit.
You have to draw out that chart first. And then, so you'd have to convert it to binary. And then you'd have to use the sign and magnitude at the very leftmost spot.
Okay, so let's tell me if you want to convert the number 9 here to the size and magnitude of the 8-bit here, what is it? What is it? What is it in the size and magnitude format of the number 9 in the 8-bit memory?
Would it be 0, 0, 0, 0, 1, 0, 0, 1?
0, 0, 0, 1, 0, 0, 1, right?
Yeah.
Okay, so now see how it works. The first one, if you store in the 8-bit memory, you have 1 bit here is a sign, right? And you know that it's a positive, so it's a 0, it's correct. Right? So now you're working with the magnitude here. The number 9, when we convert it to the binary, you have 1, you have 0, you have 0, 0, 1. That is number 9, right? And now in order to make it up for the 7-bit here, you have to add 1, 2, and 3 to the left of that. That's why you have to put 0, 0, 0 here. You have the 7-bit magnitude. And one more bit 0 here is the size. That's why you have 0, 0, 0, 0, 1, 0, 0, 1 here. That is correct answer, right? So now if you have the number negative 13 here, so how we convert it to the size and magnitude here in the 8-bit memory?
Well, you have like 1 on the far left, like
So first you'd convert it to 8-bit, right?
Yes.
Yeah.
Would it be 11110010?
1 1 1 1 0 0 1 0.
Yeah.
Any other answer for that? Okay, so if you work as a sign and magnitude, remember you always have a 1 bit for the sign here, right? So this one negative is correct. Number 1 is correct here, right? And in this case, forget about the sign here. You have the 13 in the magnitude. So what do you have? When you convert 13 into magnitude here, what do you have?
Um, 1 1
This one, right?
0 1. Yes.
Yes. So we see this one is the 13 in magnitude, and you already have the 4 bit already. You already have the 4 bits. Now you have to make it up to the 7 bit of the magnitude. That's
Add
why you go here
3
0
zeros to the far left. Yes.
and 1 at the beginning is the sign. So when you convert negative 13 to the sign magnitude, you have 0. Sorry, you have 1 0 0 0 1 1 0 1 here. Got it?
Wait, I
I
thought
got
you
it now.
flipped the
Hello?
digits.
Sorry, say again.
I said I thought you flipped the digits when it was a negative.
No. When working with a 1 complement, it is you have to flip it. But for the sign and magnitude, you just do it normally. Right? You have 1 bit. You have 1 bit for the size, and you have the other bit is for the magnitude here. Okay. So now you have a sum of the format here. You have to remember the first one is unsized that converted normally. The second one is sign magnitude. And you have 1 bit for the size and all the other bit is for the magnitude. Now, so the one you are talking is that it is the 1 complement here. You move to the third one. The third one is the 1 complement. So in the 1 complement, also you have 1 size. Sorry, you have 1 bit for the size here. 1 bit for the size. And when working the 1 complement, if it is a positive number, you just convert it normally. And if it is a negative number, you reverse everything from 0 to 1 and from 1 to 0 here. Okay. So now, another example. If you want to working with the 1 complement, and if you want to convert the number 18 here, positive 18 here, to 1 complement in the 8 bit here. So what is it? What do you think? If you have the positive 18, and if you want to convert it to the 8 bits of the 1 complement here, what is it?
So, so 1. So first you convert positive 18 to binary to 8 bits. So you got 1 0 0 1. I think, is it? Oh wait, 1 0 0 1 0.
You can use a calculator if you want. Yeah. So you see, if you have decimal number here, 18, right? So you see, you have the 1, you have 0 0 1 0 here, right?
Yeah, so that's what's up.
So now it's a positive, right? So you just convert it normally. You have the 1 bit, it's a positive here, 0 here. And the 7 bit, now you see, you have 18 here. So that's why you have 1 here is a 16. 0 here, 8. 0 here, 4, right? 1 here is 2. So, sorry. Oh, why I cannot? Yeah. And you have 0 here. You see, 16 and 2 here, 18, right? So you have 1, 2, 3, 4, 5 already. You add 2 more 0 here. And 1 more 0 to the side. So you see, when you convert it in the case of the positive, you just convert it normally. 1 bit for the size, and all of them is, you see, you get the same when working with the size and all inside here, right? So remember, for every format, when you convert for positive, they are always the same. They're always the same. Just convert it normally and adding 0, leading 0 to make it up to 8-bit memory or 16-bit memory here. So now
you flip the numbers, or like you convert it the other way, or reverse the binary numbers whenever you're doing the negative?
Yes. So whenever you have the negative, you convert, you revert it. But for the
Okay.
positive, always do the same.
Okay,
The
cool.
positive, if you're working with the unsigned or sign and magnitude or one complement or two complements, they're always the same.
Okay, thanks.
So now think about if you have the negative 18, right? You have a negative 18. So for the first side here, you have negative, you have number 1 here, right? And for all of the bit here, you just revert from 1 to 0 and 0 to 1. So we have 1 here, you have 1 here, you have 0, you have 1, 1, 0, and 1 here. That is a negative 18. Right? And if you look at in this one, and if you want to revert this to the decimal, you can see this one is negative here. Right? And if you want to convert it back to decimal, again, you see if it's negative, you have to reverse everything back. You have 0, you have 0, you have 1, you have 0, 0, 1, 0, and after that you convert it back to the decimal, and you have 18 here. So this one is negative 18. You got it?
Yes.
Yep.
So now the next one here. Okay, sorry, one thing I forgot to mention here. So for the sign and magnitude here, you have a problem with when you want to represent the number 0 here, right? So we think if you have the positive 0, so we see all of them 0 here. 1, 2, 3, 4, 5, 6, 7, and 8 here. That is the positive 0. And if you have 1 here and you have 0 here, that is a negative 0, right? See, that is negative 0. Because you see, this one is a sign, positive, and the magnitude here, 0. This one is a sign, it's a negative, and the magnitude here, 0. So you see, for the sign and magnitude, you have two ways to represent the number 0. So that's why it's very, very confusing for the computer here. For the one complement also, if you have everything 0 here, see, this one is a sign, right? That is a positive. And this one, you convert it here, 0 here, right? So now what happened if I have numbers 1, 1, 1, 1, 1, 1, 1, and 1 here? So what happened? You see, when you have number 1 here, you have idea that it's a negative, right? And in the case of negative, you know that if you want to convert it, you have to reverse everything. So you have 0, you have 0, 0, 0, 0, 0, 0 here. And this one, when you convert it to the decimal, you have the 0 here, right? So we see in the case of the one complement also, you have two ways to represent the number 0. You have all of them number 0 or all of them number 1 here. Again, it's very, very confusing here. So the next one is a 2 complement here. 2 complement. So in the case of 2 complements, the first one, the positive always the same. Do it normally. The positive always the same. Do it normally. And in the case of negative, the first one, you have to convert it to the 1 complement. The first one here. The second one, from the 1 complement, you add to number 1. And the third one, if you have overflow here, you just discard the left mode here, the left mode bit. Okay, so now see how it works with the 2 complement here. So if I want to convert a positive 21 here in the 8-bit memory, what is it?
Is it a 1, 1, 0, 1, 0, 1?
You store in the 8-bit memory of the 2 complement here. So if you have positive 21, what is it?
It's 1, 0, 1, 0, 1.
You have the positive 21 here. The first bit always number 0.
Oh yeah, right.
Yeah, that's the thing you have to clarify at the beginning here.
Is it 0, 0, 0, 1, 0, 1, 0, 1?
Yes.
0, 0, 1, 16 here, right?
Yeah.
0, 0, 1, 0, 1, 0, 1.
So you have the 64, you have 0 here, you have 1 here, 16, right? 16, 8 here, 4 here, 0, 1 here, right? Is that correct? Yeah. Now you see, positive always the same. The positive always the same. You just convert 21 here, and you adding all of them 0 to the left here, right? You see, you have the 0, 1 here. Sorry, you have 1, 0 here is a positive, and all of them you add 2 more 0 to the left to make it to the 7 bit here. Okay, so now if I want to make if I want to represent the two complement of the number negative 27 here. So what do you think? In the 8 bit here. It's 8-bit memory. Negative 27.
Negative 27?
Yes, 27.
Would it be 1 1 1 0 0 1 0 0?
1 1. Can you tell? Can you? Yeah, 1
0 0
0 0 1
0 0.
0 0. Okay, now see if it's correct or not, right? So for the negative, the first one is the sign here, right? The sign here, the number 1 is correct. For the negative 27, you have the 27 here, right? So the next step, you have to convert the 27 to the binary. So for the 27, you have the 16, you have 8 here, the 24 already, right? You have 0 here, you have 1 and 1 here, right? So you have the 5 bit already, right? So you have to make it to the 7 bit, you have 0 0 here. That is magnitude, right? And now the first step, you have to convert it to the one complement. So you have to reverse it here, right? You have to reverse it. That's why you have 1, you have 1, you have 0, you have 0, you have 1, you have 0 0 here, right? That is one complement here. Now for the two complements, the first step is one complement. The two complements, the next step, you have to add it to 1 here. All right, so we have to add it to 1 here. So instead you add it to 1, you have 1 here. So what happened? 1 and 1, you have 0. Right? 1 and 1 and 0, you have to carry out 1 here. That's why you have 0 and 1 here, you have 1 here. All right? And this one you have 1, you have 0, 0, 1, 1 here. All right? And this guy, you don't have the overflow, so that keep it the same here. So you see that if you want to convert the negative 127 here to the 2 common, you will have the 1, you have 1, copy it here, 1, 1, 0, 0, 1, 1, 0 here. Is that correct?
Yeah.
Oh, this one, sorry, this one is 0 here, right?
Yeah,
Yeah, sorry, my
I thought I was right.
Right.
Yeah. Sorry, my mistake. So you have 0 and 1, you have 1 here, right? And you have 0.
Yeah.
Yeah. So this will be 1 1 0 0 0 1 0 here. Is that correct? Okay, so now see 27, right? You have 27. You have this one is 16, 8 here. You have the 24. You have 26, and you have 27 here. The first step is a magnitude here, right? Then the first step, that's the first one. Now the next one, you have to reverse everything to have the one complement, right? Yeah. So you have 0, you have 1, 0, 1, 1, 0, 1, 0, 0, 1, 1, 0. 1 0 here. That is the one complement. Now for the two complement, you have to add number 1 here. So we have 0 and 1. You have 1, 0. Oh, this one you have 0 here. You have 1, so you have 0. Why is it very confusing here? Let me delete everything here. Okay, so now we see you have a 0 and 1. you have 1, right? After that, you have 0, you have 1, you have 0, 0, 1, and 1 here, right? That is the 2 complement, and of course, you have 1 bit here is a sign. So negative 27, when you represent in 2 complement, you have 1, 1, 1, 0, 0, 1, 0, 1 here. Is that correct?
Yeah.
Okay. Now, if you want to see the how is the number 0 work here, so we see if you have the positive number 0 here in the 8 bit, what is it in the 2 complement? Number 0 positive.
0,
The,
0.
Yes,
zero,
that's
zero.
it normally, right? All of them the number 0 here. All of them number 0 here, right? So now what happened if you have negative 0 here? What is it? Negative. The first side is number 1, right? The side here is number 1. And how we convert the negative 0 to the 2 complement here?
So you're gonna have like we're gonna have number 1 on the corner far left.
Okay, so now see, you have the negative 0, right? So the side here number 1, and the magnitude here, the first thing is everything is 0 here, right? The next step is 1 complement. You convert it to 1 here. All of them number 1 here, right? Now, in order to do with the 2 complement, you have to add to number 1 here. So we see 1 and 1 you have 0, carry out 1, 1 and 1 you have 0, carry out 1, 1 and 1 you have 0, carry out 1, 1 and 1 you have 0, carry out 1, and keep going here, 0, 0, and you have 1 bit here. That's the second one. And remember, in the case of the overflow, this one, you see, sorry, you have 0 here. In this case, you will have the 9 bit here, right? It's not 8 bit anymore. So in the case of overflow, you remember that you have to discard the leftmost bit here. So in that case, you just drop it this side, this one here, right? Just drop this one. So that's why you have everything 0 here. You have everything 0 here. Okay, see the positive and negative, all of them the same. All of them is number 0. So that's why by using the 2 complement here, you are able to represent the number 0 in one way only. So that normally for the computer, they use the 2 complement system here. Okay, so that is everything about the integer representation. So remember, you have 4 types here. The first one is the unsigned here. The second one, you have the size and magnitude. Third one, you have 1 complement. And the fourth one, you have 2 complement here. Okay, that is everything about the whole integer. Now, what happens if you want to represent the number of the floating number here? So think about if you want to do with the 8.30 here, 8.3 here. Okay, so in the case of a floating point, they break it down into 2 portions here. Sorry, actually the 3 portions. You have the integer, the whole number. You have binary point, and you have fractional point here. Sorry, you have integer part. You have the binary part. Sorry, binary point, and you have a fractional point here. And if you remember about the base 2, right? So you have when you break it down into multiple column here, you break it down into multiple column. So think about this one. You have the number 0, the column 1, the column 0, column 1, 2, and 3 here. And when you move to the right, you have -1, you have -2, and you have -3 here, right? So if you think about if you're working with the decimal, right? So for this one, you have the base 10, you have 10 raised to 0, 10 raised to 1, 10 raised to 2, and 10 raised to 3. This one, 10 raised to -1, 10 raised to -2, and 10 raised to -3. And when we convert this one, you have 1 here, you have 10, you have 100, and you have 1000 here. And this one also, you have 10 raised to -1. That means 1/10, right? 1/10 is that mean you have 0.1 here. You have 0.01 here, and you have 0.001 here. Okay. So now think about if we want to represent the number 85.56 here. So actually you have the 8 of 10 here, right? 8 here. You have the number 5 here, and you have 5 here, and you have 6 here. So we see when we convert 8 times 10 plus 5 times 0.1 and plus 6 times 0.01 here. So you see you have 85.56 here. Okay, that is when working with the decimal. And the same apply to the binary also, right? But instead of the by 10 in the binary, you have the by 2 here. So we see you also have a multiple column here. And this one. We see, so think about this one, you have 0, you have 1, you have, sorry, and you have 2, you have 3, you have -1, -2, and -3 here. And remember, when working the binary, they are by 2. That's why you have 2 raised to 0 here, 2 raised to 1, 2 raised to 2, and 2 raised to 3, and 2 raised to -1, 2 raised to -2, and 2 raised to -3. So we see 2 raised to 1, you have 1 here. You have 2, you have 4, and you have 8. This one, 1/2, right? That's why you have 0.5 here. This one, 1/4, you have 0.25 here. And this one, 1/8, you have 0.125 here. Okay. So when you convert from the decimal to the from decimal to the binary, it's the same, right? So we think about if you want to convert the number 8.3 here. So we see you have 8, right? You have number 8, right? You have 1 here. You have 0, 0, 0 here. Right? So when you convert 1 to the binary, you have the 8 here, and you have binary point. And now for the 3, right? So actually you have 0.3 here. Right? Now you do everything the same. You have to work from. You have starting everything from the fractional part here, and then we do the same. You have to move from the left to the right. Right? So the first one here, when you compare 0.3 and this one, you have 0.5, you less than, right? So in the case of less than, you put the number 0 here. Now we still have the 0.3, you move to the right, you have this one is 0.25, 0.3 here greater than. When you have greater than, you put number 1 here. So when you have the number 1, actually you have to minus it to 0.25 here, and you have 0.05 left, right? And you move to this one, you have 0.05 less than 0.125, you have put the number 0 here, and keep doing it. And if somehow they asking you that you need only 3 number, in the fractional part, so we can stop here. You can stop it here, even that they are not reaching the 0. So you see, if you want to convert 8.3 here into binary, you will have this one here. It's a integer part here. You have 0, 0, 0. Sorry, you have 1, 0, 0, 0, and binary point. And for 3 here, you will have 0, 1, 0 here. Okay, it makes sense.
Yep.
Okay, that's all. I think that's all. That's all. Everything I want to review. Actually, you have some kind of the scientific notification or some kind of that, but it's very simple. You know that whenever you want to shape it to the right, whenever you want to shape it to the right, you have the negative, and when you move to the left, you have the positive here. What is it? Any question from you? Let me know.
Not now.
This might be a weird question, but when do computers differentiate, like when they use the different metrics for like the complementary?
Say again.
Like so when do the computers like actually use the different, you know, forms of the different metrics as far as like complementary or second complementary? Like
Okay, so actually the computers they use the 2 complement here. That is the only system that is able to clear to represent number 0 here. In any other sorry. In any other representation, you see that it's quite confusing when you represent number 0 here. Right? So actually for the computer, they use the 2 complement here.
Oh,
But in order to understand the 2 complement, you have to understand the size and magnitude. You have to understand the 1 complement, right? So that's why you have a long, long way until to get to the 2 complement here.
okay.
Okay, so I think this video is a good one.
Hi, my name is Lamore Free, and I'm an engineer here at Adafruit Industries. And this is where I do engineering and design, and I design circuits for fashion and music and technology.
My name is Federico Gomez Suarez, and I'm a software developer with Microsoft Hack for Good. And I look into using technology to help us solve some of the big social problems of our times.
You may have heard that computers work on ones and zeros, or you may have seen scary looking visuals like this. But almost nobody today actually deals directly with these ones and zeros. But ones and zeros do play a big role in how computers work on the inside.
Inside a computer are electric wires and circuits that carry all the information in a computer. How do you store or represent information using electricity?
Well, if you have a single wire with electricity flowing through it, the signal can either be on or off. That's not a lot of choices, but it's a really important start. With one wire, we can represent a yes or a no, true or false, a 1 or a 0, or anything else with only 2 options. This on-off state of a single wire is called a bit, and it's the smallest piece of information a computer can store. If you use more wires, you get more bits. More ones and zeros, with more bits, you can represent more complex information. But to understand that, we need to learn about something called the binary number system.
In the decimal number system, we have 10 digits from 0 to 9, and that's how we've all learned to count. In the binary number system, we only have 2 digits, 0 and 1. With these 2 digits, we can count up to any number. Here's how this works. In the decimal number system we're all used to, each position in a number has a different value. There's the 1 position, the 10 position, the 100 position, and so on. For example, a 9 in the 100 position is a 900. In binary, each position also carries a value, but instead of multiplying by 10 each time, we multiply by 2. So there's the 1's position, the 2's position, the 4's position, the 8th position, and so on. For example, the number 9 in binary is 1001. To calculate the value, we add 1 times 8 plus 0 times 4 plus 0 times 2 plus 1 times 1. Almost nobody does this math because computers do it for us. What's important is that any number can be represented with only 1s and 0s, or by a bunch of wires that are on or off. The more wires you use, the larger the numbers you can store.
With 8 wires, you can store numbers between 0 and 255. That's 8 ones. With just 32 wires, you can store all the way from 0 to over 4 billion. Using the binary number system, you can represent any number you like. But what about other types of information, like text, images, or sound? It turns out that all these things can also be represented with numbers. Think of all the letters in the alphabet. You could assign a number to each letter. A could be 1, B could be 2, and so on. You can then represent any word or paragraph as a sequence of numbers. And as we saw, these numbers can be stored as on or off electrical signals. Every word you see on every web page on your phone is represented using a system like this. Now, let's consider photos, videos, and all the graphics you see on a screen. All of these images are made out of teeny dots called pixels, and each pixel has a color. Each of the colors can be represented with numbers. When you consider that a typical image has millions of these pixels, and a typical video shows 30 images per second, and we're talking about a lot of data here.
Every sound is basically a series of vibrations in the air. Vibrations can be represented graphically as a waveform. Any point on this waveform can be represented by a number. And this way, any sound can be broken down into a series of numbers. If you want higher quality sound, you would pick 32-bit audio over 8-bit audio. More bits means a higher range of numbers.
When you use a computer to write code or make your own app, you're not dealing directly with these ones and zeros, but you will be dealing with images or sound or video. So if you want to understand how computers work on the inside, it all comes down to these simple ones and zeros and the electrical signals in the circuits behind them. They are the backbone of how all computers input, store, process, and output information.
Video. Yeah, this one also.
One of the coolest things I've discovered about circuits is circuitry can be an art form. Like if I have a creative idea, I can get that creative idea out using circuits. So if you have ideas, you can use technology to make those ideas come to life. Every input or output of a computer is effectively a type of information, which can be represented by on or off electrical signals, or ones and zeros. In order to process the information that comes in as input and to make the information that's output, a computer needs to modify and combine the input signals. To do this, a computer uses millions of teeny electronic components, which come together to form circuits.
Let's take a closer look at how circuits can modify and process information that's represented in ones and zeros. This is an incredibly simple circuit. It takes an electrical signal, on or off, flips it. So if the signal you give it is a 1, the circuit gives you a 0. And if you give the circuit a 0, it gives you a 1. The signal that goes in is not the same as the signal that comes out, and so we call this circuit not.
More complicated circuits can take multiple signals and combine them and give you a different result. In this example, a circuit will take 2 electrical signals. Now, each one might be a 1 or a 0. If either of the signals coming in is a 0, then the result is also a 0. This circuit will only give you a 1 if the first signal and the second signal are both a 1. And so we call the circuit AND. There are many small circuits like this that perform simple logical calculations. By connecting these circuits together, we can make more complex circuits that perform more complex calculations. For example, you can make a circuit that adds 2 bits together, called an adder. This circuit takes in 2 individual bits, each one a 1 or a 0, and adds them together to calculate the sum. The sum can be 0 plus 0 equals 0, 0 plus 1 equals 1, or 1 plus 1 equals 2. You need 2 wires coming out because it can take up to 2 binary digits to represent the sum. Once you have a single adder for adding 2 bits of information, you can put together multiples of these adder circuits side by side to add together much larger numbers.
For example, here's how an 8-bit adder adds the numbers 25 and 50. Each number is represented using 8 bits, resulting in 16 different electrical signals that go into the circuit. The circuit for an 8-bit adder has lots of little adders inside of it, which together calculate the sum. Different electrical circuits can perform other simple calculations like subtraction or multiplication. In fact, all the information processing your computer does is just lots and lots of small, simple operations put together. Each individual operation done by a computer is so simple, it could be done by a human, but these circuits inside computers are way faster.
Back in the day, these circuits were big and clunky, and an 8-bit adder could be as big as a fridge, and it would take minutes for them to perform a simple calculation. Today, computer circuits are microscopic in size and way faster. Well, why are smaller computers also faster?
Well, because the smaller the circuit is, the less distance the electrical signal has to go. Electricity moves at just about the speed of light, which is why modern circuits can perform billions of calculations per second.
So, whether you're playing a game, recording a video, or exploring the cosmos, everything you could possibly do with technology requires lots of information to be processed extremely quickly. Underneath all this complexity is just lots of teeny little circuits that turn binary signals into websites, videos, music, and games. These circuits can even help us decode DNA to diagnose and cure disease. So, what would you like to do with all these circuits?
Okay, so I think this was the two videos very interesting. You don't have to watch all video in the reading here. Some of them, honestly, I see that very boring. And let's see. Okay, so let's see. Okay, I think this one is good. All of them here already covered in my slide, so I don't have to do it. Okay, so far we already know how the computer understand when we enter the number, right? So we can enter the number, so the whole integer number or floating point or fractional number here. Right? We will know how to process it and how to speak here. And the thing is that is if you look on the keyboard, beside from the number, you also have some kind of the character, right? So the question here is that how the computer understand that if I enter the character A or B or C or D here. So you have multiple ways to decode from the character to the way that computer process here, and one of the most common is the ASCII code here. Okay, so in the ASCII code, you see that for each of character also they will convert it to the binary so the computer will understand what is it. So think about normally if you have the ASCII, normally if you have the normal ASCII, you have the 7-bit here. Yes, 7-bit. So we think if you have the 7-bit in combination here, sorry, you have 7-bit. So actually you will have a 2 raised to 7. You will have 128 of character here. You have 128 character here. Okay. And if you look on this one is a conversion between the ASCII code here, right? So you can see some of them. You have the 65 decimal. You have 65 decimal. Actually, it is a character capital A here. And when you convert the 65 here to the binary, you would have a 1000001 here, and so on. You have the B, C, and D, and you have the C. Right? So we have A here. Lowercase a is the 97. So basically, when you compare the character in the ASCII here, the lower number of the decimal it is, right? So lower order bit. Think about that. So I think we will compare the character in the module 3. But for now, you just need to understand that in order to represent the character in the computer, normally they use ASCII code here. So for each of the character, they will have the they have the appropriate the number of the decimal or the binary here. So now let me come back to the module. This one last week, sorry, on Tuesday we did it, right? I'm not. Okay, this one I very okay. Here's a question here, right? If the ASCII is, you see, you have the 0 1 1 0 0 1 1 0. So they're asking you that what is the ASCII value of that? So you can look it up on the table here. Sorry, if you look it up on I close this one, right? You can look it up on this one. You see, you have zero. Sorry, you have. So this one when you convert it to the, you have 164, right? You have 64 here. You have
106.
96, right? 96, and you have 4 here. Is a 100, and you have 102, right? So this one 102 in decimal, and you can look it up. What is it?
Right.
Yeah, 102 in decimal here. You have F here, right? You have F. You have this one is F here. Okay, that's the way you're working with the conversion from the ASCII or binary to the ASCII here. Okay, so now see, you're working with you're working with homework assignment. See what you have. Okay, so for each of them, you have to remember what is the requirement. For this one, they are the 8-bit sign and magnitude. Right? So we just convert it. So for the positive, they convert it normally. And you remember that you have stored in the 8-bit here. So in the case that when you convert, you don't have enough 8-bit, remember that you have to adding 0 to the left to make it up to the 8-bit here. Right? The same is this one. You have 1 bit, it's number 1 at the beginning for the size, and you convert the 29. And after that, if you don't have enough bit, you have to add number 0 to the left to make it up for the whole of the 8-bit here. Is that this one you have to convert it to the hexadecimal, right? So you know that in the case of hexadecimal, you have to group every 4 bit together from the right to the left, right? So we have to convert every 4 bit together from the right to the left. And if you look it back in the slide last time, let me see where you have it. Okay, so if you look on the hexadecimal notation here, you know that you have to group every 4 bit together from the right to the left, and in the case that you don't have enough for the 4 bit, you have to add 0 to the left here. Okay, so you come back to this one, you group every 4 bit together, convert what is the hexa, and what's the hexa. You do the same with the second one here. Now you write the hexadecimal representation of each of the decimal. Okay, so if you have the 12 in the decimal, so what is this in the hexadecimal? You have A is 10, right? You have B is 11, and the C.
C? Is
Yeah.
it C?
Yes. And of course, you can convert it manually, or you can use a calculator. I don't care about that. And now that you have calculator, so we have 160 here. You see hexadecimal, you have A0 here, right? You have A0. So 1 second. Write the decimal value of the following. Okay, so for this one, you convert from binary to decimal. It's very simple. This one convert from binary to hexadecimal notation. Again, you group every 4 bit together, right? And you convert it to the hexadecimal. Hexadecimal notation into the decimal. You can use the calculator to convert it here. I don't care about that. Write the binary representation of each of the following. Okay, convert from the decimal. Decimal to the binary to the binary to the binary to the binary here. Question 8. Okay, that's the thing, right? That's the thing. You have to convert the decimal fraction here. And if you remember about what we did with the decimal fraction, okay. Okay, so we remember about the decimal fraction when we're working with the fraction part. You see, it's starting with the column of the -1, -2, -3, 4, 5, and 6. Right? And since it is by 2, so we have 2 raised to -1. You see, 2 to -1, 2 raised to -2, 2 raised to -3, 2 raised to -4, 2 raised to -5, and 2 raised to -6. So we have 2 raised to -1. That means 1/2. You have half. 1/4. You have fourth. 1/8, you have this 1/8 here, right? You have 1/16, 1/32, and 1/64. And you do the same. You just do everything from the left to the right. Whenever you have greater than, you put the number 1, and whenever you have less than, you put the number 0 here. Okay. So now see, what about that? You have 6, 8, 75 here, right? 6, 8, 75. Okay, so now see, you move everything from the left to the right. You have 6, 8, 75 greater than 0.5 here. You put number 1 here, right? So you have to minus it to the 0.5. Sorry, 0.5 here. So we have 1, 8, 75 left, right? You have 1, 8, 75 left. You move, you move to the right. You move to the right here. See, for this one, you have to compare to this one here, right? You have to compare to this one. 1.1875 less than this one, you put 0 here, right? So now move to the right again. You compare to this one, 0.125 greater than, you put number 1 here, right? So you have to minus it. You have to minus 0.125 here. So what you have left? You have 0.6.25 here, right? So now to that perfectly matches this one. Yeah, you see, perfectly matched. So that's why when you convert 0.6875 to the binary, you will have the 0.1011 here. Okay. You got it? Hello? Yeah, so we do the same. You do the same with the second one. Now you convert the decimal integer to the 8-bit unsigned here. 8-bit unsigned, very simple, right? And if somehow, if you have the overflow, you have to tell with the overflow here. But for the 8-bit unsigned, you just convert it normally. Decimal value of each following binary. So you have to convert from binary to decimal. You have to convert from binary to decimal. What is a hexadecimal number? Immediately proceed the number. Okay, so what do you think? What is a hexadecimal? Come right before the E9 here. What do you think?
8.
Yes, E8, right? E8, it come right. So what do you think? If you have 200 here, which one come right before that?
199.
Is that correct?
The hex. And hexadecimal.p.
Yeah, you have the hexadecimal here, not the decimal. Right? So which come right before the 200 here in hexadecimal? What do you think? Okay, so let me tell you. You remember that for the hexadecimal, you have everything from 0, 1, 2, 3, 9, A, B, C, D, E, and F, right? So now for if you have a 200 here, the one right before that, you have to minus 1 here, right? So what do you think? If you have 0, you minus 1, what come here? Right? You have F here. You borrow 1 from that one, right? You borrow 1 from this one. So again, you have to minus 1. And you see, if you light cycle here, you have F here. And you have to borrow 1 from this one. So now we have a 2, you minus 1, you have 1 here. You got it? Hello?
Good.
Yeah. So remember for the hexadecimal, you have everything from 0 to F here. Right? 0, you cannot minus for the 1, so you have to borrow 1 from this one. And when you from 0 here, you minus 1, you have to come back to the circle here. You have F here. You borrow 1, 0, minus 1 again, you have F, and borrow 1, 2, minus 1, you have 1 here. Okay, that is the one come right before 200 here. Write the decimal value of the following. So you just convert this one from hexadecimal to decimal. And again, okay, here's the ASCII, right? So here's the ASCII here. So you have to convert this one. What is the character? What is the character? What is the character? And what character? You put it down here. And what's the character? What's the character? You put it here. Again, it's the same with this one. You just look it up. You just look it up into the conversion of the ASCII here, and you write down to the answer here. Write the decimal value. Okay, convert it from the hexa to the decimal. Convert from hexa to decimal. Write and binary here. Convert to binary. Very simple. Okay, so for this one, you see you have to convert what is the character S, right? So we look it up, the capital S here. The capital S. Yeah, right? So we have to copy this one. And the lower key, the lower I, you have to copy this one and move on, right? You move on. SIL. And remember you have the dot here. You also have to put it into the ASCII code here. So see where's the dot. This one, right? This one is the dot. I'm not really sure. Or you can look it up. Yeah, I think this one. Yes, this one here. Okay, so just copy it and paste it here. And again, for this one, what is this? What is it? Put it down here. Okay, this one is the pi 2 complement, right? So you know that you have 8-bit memory here. For the positive, just do it normally. For the negative, is the first thing you have convert it to the 1 complement and add to 1 to have the 2 complement here. And ASCII, that do the same. Very simple. 20 question only. Okay. Do you have any question for the homework, or if you want me to work with anyone, let me know. If anyone is that you think that you need my help, just let me know. I can work with you. Any question?
Nope.
Nope.
Okay, so you think you were good with the homework and assignment? Okay, so if you don't have a question, you can end the class now. Remember that anytime, if you need my help, if you have any challenge with the homework, let me know. You can send me the email, or I can work with you to sort it out here. So if you don't have a question, you can end the class now.
Okay.
Have
Have a good one.
Okay.
weekend.
Okay. Thank you, guys.
Thanks.
I'll see you guys on
On Tuesday.
Thursday. Bye bye.